can't carry signals over DC, it has to be over AC and stuff, so AC is kind of our, for signals and all that. And then our solid state devices, then that's where we're going to use it for, rectifying our AC voltage into DC voltage, making converters, amplifiers, operation on op amps, which we're going to get into the next last 4 weeks of the program. So the solid state devices are, remember when we're looking at, when we first started out in DC, we had conductors and insulators, and the conductor had one electron on the valence ring, and that made that one electron free, so we had, had all our protons in the center, and then our rings on our atoms, and then on the, if we had a good conductor, it only had one electron on that outer valence ring. All right, you guys stop talking for you. And so that made it for a good conductor, and then a good insulator then was one that had all its electrons on its outer valence ring maximized. So if it was the second ring out, and it had, actually I think it has, would actually have 8. Second one out would be 8. If it had 8 electrons on its outer valence ring, that made it for a good insulator. Didn't have any free electrons. It didn't want to release any of the electrons to be free moving through the wire. Whereas like this one here, this one still had enough room for 7 more electrons, and it would easily accept another electron, and it would also easily break free from this electron and bring it over to the next atom. So now the semiconductor is one that's in between these two. And it's going to have 4 electrons on its valence ring. So it doesn't really make it either a good conductor or a good insulator. It's somewhere in between the two. It wants to hold on onto its 4 electrons, but if we give it a little push, either by heat or by voltage or something like that, we can get these electrons to break free and then move to the next atom. So on the conductor, gold, copper, aluminum, those are all good conductors. Insulators are, paper, glass, air, those are all good insulators. And then semiconductors are either going to be silicon or germanium. And those are good semiconductors, where they only have 4 valence rings, 4 electrons on its outer valence ring. And with a little push, like I said, with a little push either by heat or by voltage, we can get those electrons to jump from one atom to the other and create our electron flow. And I'm not going to go into the whole physics of it and stuff like that, so hopefully you got time to read the chapter and stuff like that. So I'm going to kind of break it out exactly what our semiconductor is. So our semiconductor, we're going to be looking at our diode first. So what our diode is our diode is going to be made up of this silicon atom. If I just have this diode as, and it looks, kind of like a large size resistor. Typically they're black and they got a ring on one end. So it looks kind of like very similar to the shape of a component. It's got 2 leads on it. If I make this diode as just out of silicone, if I put in a voltage into it, negative, positive. If I put in voltage in there, I'm going to get current to flow. I'm going to get enough voltage to kind of get these free electrons to start moving through there. And I can get the current to flow through this way if I have my polarity that way, but if I switch my polarities around, I can also get my current to flow the other way through it. Okay? So the purpose of that wouldn't do us any good. So what we really want to do is that we want to have some kind of characteristics of what this diode is going to do. And what we do with these diodes is that we kind of use them for electronic switches. So what we want to do is have it so that if I switch my polarities around, the current is only going to flow, will start to flow one way, but if I flip my polarities around on it, it's going to block the flow of current. So what they do is they take that silicon atom and they put impurities into it. And they kind of split that diode in half here. And what they do is they dope one side of it with an N-type material. On the other half, they put a P-type material. So this N-type material is one that is going to have an extra electron on it. It's going to be a little bit more electrons on its outer shell, and the P-type is going to have one less. So this one's going to only have three electrons on its valence ring, and then the N-type material is going to have 5 electrons on its valence ring. And they can be like boron. I can't even remember the chemicals anymore here. Let's take a look at in our chapter here.
724.
What is it, 774?
724.
Oh, no kidding. Yeah, so the N-type is going to be, what did it be? So on 724 there, where it says the N-type material has the 5 valence electrons: arsenic, phosphorus, antimony. So those are some of the N-type materials. The P-type materials then, which have one less, which only has 3 electrons on its valence rings, are going to be like boron and gallium. And so they divide that up, and so the N-type is going to have more electrons, and this one's going to have more protons. Let's see what they find my towel here. Grab my towel here. Oh, there it is. Thanks. So what's going to happen is that, so I'm going to kind of put it in a little easier term of what the book was trying to tell you at. So if I have this P-type material on the left-hand side, this N-type material on the right-hand side, this one's going to have more electrons, this one's going to have more protons. And I'm going to have this little gap here, this little, what's actually going to form a barrier potential, but it's going to be where our diode is kind of split in two. And so what's going to happen is that all the protons on this side of it, of this material, are going to line up on this side. All the extra protons are going to be on this side. And then all those extra electrons that were on the N-type material are all going to be on this other side. And they're going to be attracted to each other. But they're not really going to break through that barrier there. So they're going to create this barrier potential. They're going to just kind of form a gap here. And so what we can do then is that, since this is our N-type material and stuff, and they're kind of forming a gap here. They're kind of joining themselves together here and making this little barrier potential here. Kind of like our capacitors. Remember we had our 2 plates that are separated by air or paper or something like that, and all the electrons wanted to stay on one side and all the protons wanted to the other side, but they couldn't really jump that gap. That's exactly what's going on here. They really can't jump that gap, but they're all being attracted to each other and creating that barrier potential. But if we apply a little bit of energy to it, we can get that electron flow to go through. So look up my source again. And what happens is that I'm going to start pushing all these. We put a little pressure on there, and I'm going to start pushing all these electrons in there. And these electrons then are going to have enough energy to jump that gap. It doesn't take much energy because remember, it's all being, this little gap is only being separated by the silicone. So what this thing here can accept 4 more electrons, and we can push off those 4 electrons and push them onto the next silicone atom. And so what happens is that when we give it a little pressure, or put a little voltage onto it, then those electrons are going to jump that gap and then start going over to the p-type material. And they're going to start filling in what they call the holes or the protons. I call them protons, but you can call them holes. If I remove one of these things, it just becomes a hole. It means that it's going to accept 1 more electron, or it's has more protons. So all those electrons are going to start to jump that gap, and then the current is going to start to flow through. And I create myself some current. So that would allow me, so if as long as I put my more negative negative side of my battery into my N-type material, I can get my current to flow through. That's what we call our forward biasing. So that's going to be our forward biasing. And then this side here, so instead of calling it the N-type and the P-type, we also call this the cathode. And this is going to be our anode. So that's how we're going to identify it. This is going to be the more positive side. This is going to be the more negative side. And how they represented it is that the anode is going to be the A, and the cathode is going to be K. So they use K for the cathode. And so if we see the K, that means that's our cathode side. That's going to be our more negative side of our diode. If I make this side more negative than this side of my P-type material, I'll get my current to flow through. So now if I switch my polarity around on it, now, if I switch my polarity around on here, this side's going to become more negative. And what's going to happen then is that this side's going to become more negative, and what's going to happen is that all these protons are going to want to go and they're going to kind of go and be attracted to that negative side. And so they're going to start to move over to where all this, my more negative side of my voltage source is, and they're going to build up over on this side. All my electrons are going to want to go on to my more positive side, and they're going to kind of move over to the other side. And so when that does that, what happens is that barrier potential ends up widening. That gap ends up widening. And so then what it does is it has more resistance to it. It's going to stop the flow of electrons. So all these protons are going to go this way, all the electrons are going to kind of separate themselves out. And it's not going to allow for the electrons to flow. It's going to act like an open. And it's going to stop all my current flow from going through that way. So that's how it ends up acting like a switch. So if I switch my battery source around and I flip the leads around, then everything starts to go back. My barrier potential starts to get shrunk up. The electron starts jumping that gap. Current starts to flow. If I flip that battery around the other way, flip the polarities around, my barrier potential kind of starts to widen out again. All my protons go over to this side, my electrons go to this side, but they don't try jumping over to each other. They're trying to be attracted to each other's side of that diode. And so it just kind of acts like a switch depending on what our polarity is of our battery sources. Yeah.
Is this the same concept for LEDs as well?
Mm-hmm.
So I've read that if you hook an LED up backwards, it actually wrecks the light bulb.
Yes.
Only if you apply so much voltage that what we call that's kind of our reverse biasing state. But what we can do is if we apply enough voltage, so let's say right now we're in a reverse biasing. My depletion area is really large. I'm more negative on this side, more positive on this side, so I'm in a reverse biasing, the current's not flowing. But what can happen is that if I crank up my voltage so much, what I can actually have this do is I can overcome this barrier potential and start getting these electrons to start flowing through that semiconductor. But that's a reverse biasing, but it's in a breakdown mode. So what's happening is that we're actually breaking down that diode, and we're forcing those electrons so hard across that barrier potential that we're actually damaging the diode, and it'll end up burning out the diode. So yeah, you're right. It will eventually burn out the LED because you're in a reverse biasing, but then you're in a reverse breakdown of the diode. So it's actually destroying your LED. So yep, you're right. But if you just have a low voltage, we did that when we were in labs. Remember, if we had our LEDs wrong, the light didn't light up, but then we turned it around and it lit back up. That's because we never put enough voltage on there to do that reverse breakdown. Okay. Yep. So that's what. So like Corey's talking about the LEDs. When we work with LEDs, if I take this little junction here and I dope it up with some other type of chemical, like a phosphorus of some type and stuff, and if all of a sudden I start to apply a current to it, that phosphorus starts to glow. And that's where we get our LED. That LED will start to light up when we start going into our forward biasing. That phosphorus will actually start to light up. And depending on what type of material we have on there, it'll give us different color LEDs, or if we change the lens color, that'll give us different color LEDs too and stuff like that. So, yep. So that's another good example of a diode is an LED. All right. All right. So then I've been talking about this kind of barrier potential. And I like to use the word that barrier potential. That's the amount of voltage that it's going to take to get those electrons to jump from one side to the other side. And if we're talking about a silicon diode, that voltage, we call it the barrier potential because remember, what's our definition for voltage? Oh, come on!
Potential difference.
Yeah, the potential difference between 2 points, okay? So that's why we call it our barrier potential, because it's that potential difference between the 2 points. So the difference between my N-type and my P-type. And it's always going to take a consistent amount of voltage to jump that barrier. And that voltage on a silicon one is, for theoretical purposes, is going to be 0.7 volts. So silicon is always going to be 0.7 volts to jump that barrier potential. Once I get those electrons flowing, once that electron starts to flow, I'm always going to drop 0.7 volts across that. So if I take my ohm meter and I put my red lead here, my black lead here, and I measure my voltage, I'm going to measure 0.7 volts across that diode. On a germanium one, my voltage, it doesn't take as much energy to get those electrons to flow past that voltage barrier here, that barrier potential, and that's only going to take 0.3 volts. So if I measure a voltage drop across the diode and I'm only measuring 0.3 volts, it's because I got a germanium type diode in there. If I measure 0.7 volts across the diode while it's in a forward biasing, then it's silicon.
What's in the parentheses?
Oh, silicon and then germanium. Just
Okay.
yep.
Chemistry on this.
Yeah, it's without the periodic table on you guys there. Yeah. And if you really want to get into it and stuff, you can coming up with what is a P-type material and what's an N-type material. So if you're really into physics and stuff, to figure out if it's a P-type material, what you have to do is take your atomic number. So like for example, Let's see what would be a good one. I'm not even gonna try attempting. I'll just say like plus, this one here would be,
2, 8, 10.
yeah, so we'll say a plus 14. So my atomic number would be a 14 on this thing. So then if you want to find out whether if it's a P-type material or an N-type material, I want to get this one, I'm going to change it to 13, plus 13. So atomic number of 13, what I would do then would be, I'd have to go and calculate out how many rings I have. So I got, so first ring I'm going to have 2, then my second ring I'm going to have another 8, so that's going to be an atomic number of, or I'm going to have 10 electrons on the first 2 rings, and then on my outer ring then, the remainder would be the 3 left. So that would be a P-type material. So yeah, but that gets to be complicated if you want to really, but that's how you want to figure out whether it's a P-type or N-type. If it was an N-type, then this atomic number would have to be a 15, or something where I only have, where I have 5 electrons on my valence ring. You remember that from your periodic tables from back in high school there. But like I said, I don't like to talk, 2 things I'm not is a mathematician and a physics teacher. I understand it, but I can't teach it. Makes sense to me, but. Alright. Let's see here. Alright, so does that kind of make a little sense about how a diode works and stuff?
Yep.
Alright, let's get to the worksheets then. Then we'll see how these diodes actually work there when we start using our worksheets. It'll make a little bit more sense here. But yeah, now you got the physics of it, the very basic mode. Alright, so let's turn to our lecture worksheet.
Seriously?
So anyone get like arrested or anything, slapped in jail or anything over the week break or anything like that?
Tried.
Did ya?
Didn't have it over the break, it didn't happen over the break, but I almost broke the wheel off my car. Like, the first snow that
What did you run into? Slide and run into a
I went around the turn at 40, I made it to the end of the turn, and that's when the back end just kicked out. It's just like I overcorrected, that's why I got her sideways.
Yeah.
Sign. I jumped the curb and hit a sign, and that's the sign of the tree.
I could easily burned that. If I was in the car, so I was back inside, you went on a magnet, going on the road, then I went back on it, straight, 30 on a 30 mile per hour road.
Yeah.
I see, he lost control, went straight into a tree. And the passenger side was more correct.
In my book.
The other side, but the whole thing's total.
Really?
Yeah, they have silicone in there and boron and everything else, but I didn't see the germanium.